aircraft materials and processes. In this section, we will know about the nonferrous metal. Much of the metal used on today's aircraft contains no iron and is referred to as nonferrous metal. This term is used to describe those metals which have elements other than iron as their base. This includes aluminium, copper, titanium, and magnesium, as well as others. Now, A. Aluminium and its alloys. Aluminium is in its pure form is not strong enough to be used for the construction of aircraft. Pure aluminium melts at 1230 degree Fahrenheit. The strength of aluminium is increased considerably when it is alloyed with other compatible metals such as copper and zinc. When alloyed with either copper or zinc, aluminium alloy is as strong as steel, yet only 1/3 the weight. Aluminium resists corrosion by forming an oxide barrier on its surface. Aluminium alloy obtain a natural strength from heat treatment and an increased strength from cold working. The strength of non-heat treated aluminium alloys in bracket which are rarely used for primary structure bracket closed can be increased only by cold working. Now number 1, alloying agents. One way the various types of aluminium alloys are classified is by their major alloying ingredient. The elements most commonly used for aluminium alloying are magnesium, manganese, copper and zinc. Example of alloys made from the various metallic elements are magnesium 5056-H32, manganese 3003-S24, copper 2117-T4 and zinc 7075-T6. Wrought aluminium alloys may be identified by a 4-digit index system. This system breaks aluminium alloy down into groups identified by the first digit, which reveals the principal alloying agent. Now A. 1000 series. These represent commercially pure aluminium, 99% or higher purity. The 1000 series offers high resistance to corrosion, excellent thermal and electrical properties. It is easily worked but is very low in strength. Now B. 2000 series. When aluminium is mixed with copper, certain metallic changes take place in the grain structure. When copper is the principal alloying agent, the product will be identified as a 2000 series alloy. These changes are for the most part in bracket good and result in greater strength. The opposite reaction to alloying can produce a metal which now becomes susceptible to corrosion. Because of the processes it must go through to become stronger. Safeguards have been developed to offset the destructive side of alloying aluminium and copper by stabilizing its internal grain structure through an additional process called precipitation heat treatment. The types of aluminium alloy used most frequently for aircraft constructions are from the 2000 series of sheet metal materials. One of the most commonly used is the Reheat alloy 2117-T4. The other alloy often used as skins and rivets are 2017-T and 2024-T. Now C. 3000 series. The 3000 series uses manganese as the principal alloying elements and is generally considered non-heat treatable. The most popular variation is the 3003, which offers moderate strength and has good working characteristic. Now D, 4000 series. 4000 series aluminum is alloyed with silicon which will lower the melting temperature. This result in an alloy that works well for welding and bridging. Now E, 5000 and 6000 series. Magnesium is used to create the 5000 series alloy. They have good welding and corrosion resistant characteristic. If silicon is also used with the magnesium, the result will carry the 6000 series designation. The 6000 series has medium strength with good forming and corrosion resistant properties. Now F, 7000 series. When parts require more strength and not much forming, then much harder aluminum alloys are used by aircraft builders. A much harder aluminum alloy used for aircraft construction were those from the 7000 series. The 7000 series aluminum alloys are made harder and stronger by the addition of zinc. Some widely used forms of this zinc influenced aluminum alloy are 7075-T6 and 7178-T6. Recently, a new addition to the 7000 series alloy was made in bracket especially for rivet stock called 7050-T73. Now, number 2 is heat treatable alloy. Now, the term heat treatment when applied to aluminum alloys means the metals is made harder by the process. The alloys mixed with copper such as 2024-T4 are given a natural heat treatment process. Those alloy mixed with zinc like 7075-T6 first receive natural heat treatment, after which an additional process called precipitation heat treatment is given. The precipitation heat treatment stabilizes the grain structure and reduces the possibility of corrosion. Those alloys containing copper obtain their strength by the diffusion of copper into the aluminum grain structure. The diffusion of copper into the grain structure causes the aluminum alloy to harden. The grain structure of thick aluminum alloy containing copper can eventually fall if it is improper heat treated. Please go to the chapter on corrosion, which I will be referring later, about the form of corrosion which can happen when the metal is improperly quenched. A widely used aluminum alloy containing zinc is 7075-T6, which has a tensile strength of 77 ksi and the bearing strength of 139 ksi. The alloy 707-T6 is a very hard metal which is difficult to bend over normal radii. A very strong and much used zinc type alloy is 7178-T6, which has a tensile strength of 84 ksi and a bearing strength of 151 ksi. Now number 3, clad aluminum alloy. Most external surfaces of aircraft aluminum alloy aircraft are fabricated using alkyd aluminum. Alkyd is a pure aluminum coating which is applied to the surface of heat treated aluminum alloy by rolling it on under many turns of pressure. The thickness of alkyd on an aluminum alloy is approximately 5% on each side of a sheet. For example, if an alkyd sheet of aluminum bracket close 2024 T3 is 0.040 thick, 10% would be 0.004, leaving the actual thickness of the alloy at 0.036. The clad surface greatly increases the corrosion resistance of an aluminum alloy. For this reason, sheet metal should be protected from scratches and abrasion. Not only can a stress point be created, but a place for corrosion to attack the base alloy is also created. From these 2 points come the saying alloy scratch is also scrap. Now, number 4, non-heat treatable alloys. Commercially pure aluminium is identified as alloy 1100, an almost identical metal except for the addition of a small amount of manganese is known as 3003. These metals are lightweight and are not too susceptible to corrosion, but they do not have a great amount of strength and are not heat treatable. Thus, their use in aircraft is limited to non-structural components such as fairings and streamlines enclosures that carry little or no loads. Alloy 5052 is perhaps the most important of the non-heat treatable aluminum alloys. It contains about 2.53 magnesium and a small amount of chromium, and it is used for welded parts such as gasoline or oil tanks and for rigid fluid lines. Its strength may be increased by cold working. The alloy 5056-S32 was developed primarily as rivet stock to be used when riveting magnesium skins to aircraft structures. The alloy 5056-S32 contains about 2.5% magnesium. If improperly used, the rivets made from alloy 5056-S32 will fail in a short period of time. The reason for the failure is due to the lack of surface preparation prior to closing up the surface with rivets. Now, number 5, thermal treatment, in which A. Annealing. Both heat treatable and non-heat treatable aluminum alloys may be softened by this procedure. The temperature of the alloy is raised to the annealing temperature shown in this figure, and held there until the alloy has reached this temperature throughout. The metal is then cooled to 500 degree Fahrenheit at a rate of about 50 degrees per hour. Below 500 degree Fahrenheit, the rate of cooling is not important. Now, B. Solution heat treatment. Solution heat treatment is a hardening process for aluminum alloy in which the metal is heated to a temperature at which the alloying agents enter into a uniform solid solution with the matrix of the base metal. The material is held at the elevated temperature until the solution is uniform throughout, and then it is removed from the furnace and rapidly quenched before the alloying elements have an opportunity to precipitate out. Now, in the figure includes the temperature to which the various aluminum alloys must be heated for the alloying agents to enter into the required solid solution. It is extremely important that no more than about 10 seconds elapse between the time the metal is removed from the furnace and the quench, and delay will allow the metal to cool enough that some of the alloying agents will precipitate out. This precipitation occurs along the grain boundaries and drastically lowers the resistance of the material to intergranular corrosion. The metal may be heated in either a vat of molten sodium or potassium nitrate, or more commonly in a hot air furnace. Whatever method of heating used, the temperature must be controlled to within about plus or minus 10 degrees Fahrenheit of the specified temperature. When sheet metal is removed from the furnace, it may be quenched by either immersing it in cold water or by spraying it with cold water. Large forgings may be quenched in hot water to minimize the thermal shock that could cause cracking. It is normal for thin sheet metal to warp and distort when it is quenched, and it must be straightened immediately after it is removed from the quench. Heat-treatable aluminum alloys are comparatively soft when they are first removed from the quench. With time, some of the alloying agents will precipitate out of the solution and the metal will become hard and will gain strength. This aging, as it is called, occurs at room temperature in alloys containing copper, and these alloys will gain about 90% of their strength in the first half hour after removal from the quench. In about 4 or 5 days, they will become fully hard. This aging process can be slowed by storing the metals at a sub-freezing temperature immediately after it is removed from the quench. Now C. Precipitation heat treatment. There are two types of heat treatment processes used for hardening aluminum alloys: natural age hardening and precipitation hardening. Precipitation heat treatment makes the metal corrosion resistant by locking its grain structure together, when natural age hardening process does not lock them together as well. Using the precipitation heat treatment technique allow thicker and larger aluminum alloy parts to be produced without setting up the dangerous conditions for intergranular corrosion. The aluminum alloy most commonly given the precipitation heat treatment are those containing zinc. One of the most popular types is 7075-T6 to reduce the corrosion proneness of 2024-T3. It is sometimes given a precipitation treatment which makes it 2024-T86. The alloy 2024-T86 is very strong and highly corrosion resistant. Those aluminum alloy given the precipitation heat treatment are normally too hard to form over a small bend radius. Bending an alloy like 7075-T6 will usually result in cracking if the bend radius is not larger than most other forms of heat treated aluminum alloys. Now D. Strain hardening. Both heat treatable and non-heat treatable aluminum alloys may have their strength and hardness increased by cold working or strain hardening. Mechanically working metals at temperatures below their critical range, in bracket that temperature at which crystal begins to form, bracket close, result in strain hardening of the metal. The mechanical working may consist of rolling, drawing, or pressing. Non-heat treatable alloys are hardened in the manufacturing process when they are rolled to the desired dimensions, and if they are hardened too much, they can be partially annealed to the degree of hardness that is required. Heat treatable alloys may have their strength increased by rolling after they have been solution heat treated. Now E. Reheat treatment. Material which has been previously heat treated may generally be reheat treated any number of times. This may occur when using heat treated, in bracket icebox rivets. One exception to this is material that has been clad with pure aluminum. The number of solution heat treatment allowed for clad sheet is limited due to increase of diffusion of core material into the cladding with each reheat treatment. The diffusion of core material into the cladding will result in decreased corrosion resistance of the cladding. Generally, specifications will allow one of two, three reheat treatments. Now 6. Temper designations. The letter O followed by an alloy designation such as 2024-O indicates that the metal is an annealed. Annealed metal is dead soft and can be formed over a very small radii. In many cases, metal as thick as 0.063 can be bent easily by hand. The letter F following an alloy designation such as 2024-F indicates that the metal is in the S fabricated condition. When metal is formed or bent, internal stresses are set up inside the grain structure. The internal stresses are usually uncontrolled, therefore they cannot be relied upon for factual strain data. To know exactly what the strength of a piece of a metal in the F condition is, the condition must be removed either by annealing or heat treatment. Now in this, A, heat treatable aluminium alloys. Heat treatable aluminium have their condition of hardness designated by the letter -T followed by one of the mole numbers. For example, -T3 means solution heat treated, followed by strain hardening. Different amount of strain hardening of the heat treated alloy are indicated by a second digit. -T36 has been solution heat treated, and -T36 has been solution heat treated and has had its thickness reduced by 6% by cold rolling. Now -T4 solution heat treated followed by natural aging at room temperature to a stable condition. Now -T5 artificially aged after an elevated temperature, rapid cool fabrication process such as extrusion or casting. Now -T6 solution heat treated followed by artificial aging in bracket precipitation heat treated. Now -T7 solution heat treated followed by stabilizing to control its growth and distortion. Now -T8 solution heat treated, strain hardened and then artificially aged. -T9 solution heat treated, artificially aged and then strain hardened. The temper designation of non-heat treatable alloys is indicated by the letter -H followed by one or more numbers. For example, -H1 straight hardened temper produced by cold working the metal to the desired dimension. The second digit indicates the degree of hardness, just such as -H12, -H12 or -H12 quarter hard, -H14 half hard, -H16 3/4 hard, -H18 full hard, -H19 extra hard, -H2 strain hardened and partially annealed to remove some of the hardness. The second digit indicates the degree of hardness and is the same as used in the -H1 classification. -H3 strain hardened and stabilized. Now B, magnesium and its alloys. Magnesium is one of the lightest metal to have sufficient strength and suitable working characteristic for use in aircraft structure. It has a density of 1.74 compared with 2.69 for aluminium. This means that its weight only about 2/3 as much as aluminium. Magnesium is obtained primarily by electrolysis of seawater or brine from deep wells and does not have sufficient strength in its pure state for use as structural metal. When it is alloyed with zinc, aluminium, thorium, zirconium or manganese, it develops strength characteristics that make it quite useful. The American Society for Testing Metal, in bracket capital ASTM, has developed a classification system for magnesium alloys that consists of a series of letters from and numbers to indicate the alloying agents and the temper condition, which is given in the figure. In this we have the ASTM identification of AZ31A-T4 magnesium alloy with the meaning of each of the characteristic. Which each of the characters. Magnesium is used as an aircraft structural metal primarily because of its light weight. It has two rather serious drawbacks that have had to be overcome to a great extent before it was able to be used successfully. Manganese is highly susceptible to corrosion and it has quite a tendency to crack, which contribute to its difficulty in forming and limits its use for thin sheet metal parts. Magnesium is used for casting and is available in the rod form as sheet, bar, tubing and extrusion. It has excellent machining characteristic and its difficulty in forming is overcome to a great extent by forming the parts while the metal is hot. Solution heat treatment of magnesium alloys increases tensile strength, ductility and resistance to shock. After a piece of magnesium alloy has been solution heat treated, it can be precipitation heat treated by heating it to a temperature that is lower than that used for solution heat treatment and holding it at this temperature for a period of several hours. Precipitation heat treatment increases both the hardness and the yield strength of the magnesium. Now note, magnesium will burn and caution must be taken when grinding it and when taking very fine cuts while machining. If a fire should occur, it should be extinguished by smoothing it with dry sand or some other dry material that will exclude air from the metal and will cool the surface. No form of water should be used, as it will only intensify the fire. The corrosion problem is minimized by treating the surface of the metal with chemicals to form an oxide film that will prevent oxygen reaching the metal. When oxygen is excluded from the surface, no salts of corrosion can form. Now see, titanium and its alloy. Titanium is a lightweight metal which weighs 0.163 pounds per cubic inch. It has a very high strength, especially in an alloy form. Titanium is a metallic element, and when the first discovered was classified as a rare metal. In 1947, its status was changed due to its importance as a structural metal. In the area of structural metallurgy, it is said that no other structural metal has been studied so extensively or has advanced aircraft structures so rapidly. Certain forms of titanium alloys are used extensively in many aerospace applications. It has excellent corrosion resistance characteristic. Titanium has identified in an ore called rutile by an English scientist named William Groger in 1791. Later in 1791, it was found in ilmenite. In 1936, a German refugee named William Justin Crowley invented a magnesium reduction process which led to the production of metallic titanium. Rutile is an abundant raw source of titanium and can be found in large amount in beach sand and many other sources. Iron Mountain, Wyoming is an important source of titanium ore, as well as Pablo Beach, Florida. Titanium is sensitive to both nitrogen and oxygen. It has to be converted to titanium dioxide with chlorine gas and has a reducing agent, usually carbon, to be used effectively as a strong metal. Pure titanium is soft and ductile, and its weight is somewhere between aluminium and iron. It is not as lustrous as chromium or stainless steel. Titanium has an excellent corrosion resistance to salt water. Titanium is classified as alpha, alpha beta and beta alloys. These classifications are based on the specific chemical bonding within the alloy itself. The specifiers of the chemical composition are not critical to the technician. The following should be known about each classification. Now, number 1, alpha titanium alloy. Alpha alloys have medium strength of 120 ksi to 150 ksi and good elevated temperature strength. It can be welded and is used mostly for forgings. Now 2, alpha beta titanium alloy. Titanium made from alpha beta alloy result in a 2 base phase alloy. Alpha beta alloys are the most versatile of the titanium alloy. In the annealed condition, they have medium strength, but when heat treated, their strength greatly increases. This form of titanium is generally not weldable, but it has good forming characteristic. Now 3, beta titanium alloy. Beta alloys have medium strength, excellent forming characteristics and contain large quantities of high density alloying additions. Beta titanium can be heat treated to a very high strength. The grain size of titanium is defined when aluminium is added to the alloy mixture. When copper is added to titanium, it produces a precipitation hardening alloy. Titanium added to high temperature nickel cobalt chromium alloy produces a precipitation hardening reaction which provides strength at temperatures up to 1500 degree Fahrenheit in bracket 815 degrees Celsius. Precipitation hardness is a treatment which locks together particles in the grain structure of the metal, causing an increase in strength, stability and resistance to corrosion. Metals which are precipitation hardened usually lose a larger part of an malleability and ductility they may have had. Because of its high strength to weight ratio, titanium is now being used extensively in the civilian aerospace industry. After a slow start, titanium has moved from point where it was almost non-existent to where modern jet transport use 10 to 15% titanium sheet in structural area. One of the most popular forms of titanium alloy being used for aircraft is titanium 6Al-4V. The alloy 6Al-4V is used for the manufacturing of many special fasteners. Now the nickel and its alloy. Now nickel and its alloy, the number one is Monel. Monel is a high nickel content alloy that contains about 68% nickel and 29% copper along with small amounts of iron and manganese. It can be welded and it has very good machining characteristic. Certain types of Monel, especially those which contain small percentage of aluminium, can be heat treated to tensile strength equivalent to those of steel. Monel is effectively used for gears and for parts that require high strength and toughness, as well as for parts in exhaust system that require high strength and corrosion resistance at elevated temperatures. Now 2. Inconel. The International Nickel Company Inc. has a series of high strength, high temperature alloys that contain approximately 80% nickel and 14% chromium, along with small amounts of iron and other elements. Inconel is similar in appearance to stainless steel and is used for hot section parts of turbine engines because of its ability to maintain its strength and corrosion resistance under the extremely high temperature conditions. Because Inconel is used in many of the same areas as stainless steel and they are similar in appearance, a test to determine which material is being used may be necessary. A simple application of a solution of cupric chloride and hydrochloric acid is used. Using a medicine dropper, place one drop of the solution on the material being tested and allowed to remain for 2 minutes. At the end of the dwell period, the shiny spot will tell you that the material is inconel, and a copper colored spot will identify stainless steel. Now E, that is now for copper and its alloy. Neither copper nor its alloy finds much use as structural materials in aircraft constructions because of weight. But copper is primarily metal used for electrical wiring because of its excellent electrical and thermal conductivity. When copper is alloyed with zinc, aluminium and tin, it develops a high strength and is often used for bushings and for bearing surfaces. An alloy of copper and zinc is normally called brass, while an alloy of copper and tin is called bronze. Copper tubing was at one time used extensively for fluid lines in aircraft, but because of its weight and the extremely unfortunate characteristic, copper has of becoming brittle when subjected to vibration. It has been replaced by aluminium alloy. Brass fitting for fluid lines have also been replaced with aluminum alloy for most application, and with steel where high strength is needed.